All right, good afternoon, everyone. I know we'll have a few more folks trickle in, but I want to be respectful of everyone's time, so we'll get started. I'm delighted that Dr. Brandon Pitts from Purdue University is joining us today. He's an assistant for a short time longer, soon to be associate professor there. Also a director of the Next Generation Human Systems and Cognitive Engineering NHanCE lab. And he's going to tell us a little bit today about his work with autonomous transportation, which in particular has been recently honored with the first place in the US DOT's design challenge. So I'm really excited about that and excited for him about that and excited to hear what he's got to tell us.
Okay, thank you very much. I guess I'm good with sound. Okay, so thanks for the introduction and thanks for the invitation. I've been to Wisconsin before, but I've never been to Madison, so this is quite a treat for me, and I seem to have made it here after the storm last night, so even better. But I'm so happy to be able to share the work that I've been doing, actually, since I guess across the last 5 to 6 years since I've been at Purdue. So I want to make sure everyone in the back can hear me. Okay, and I do want to acknowledge someone in the room who probably doesn't want me to say this, but my first introduction to human factors related to automotives was with actually John Lee, who's in the back here, in 2008, so about 15 years ago, when he was at the University of Iowa. I was just an undergrad student who worked with him. He and Yulan Liang at the time were working on a driver distraction algorithm, and believe it or not, that set me up for a lot of what I'm going to talk to you about today. So I just want to give him his flowers while he's in the room. I've titled this talk An Autonomous Transportation Future, but you can take from it what you wish. There are some people who believe that this is very soon. There are some people who believe that this is much further away, and so I'm maybe somewhere in the middle. And so I'm going to actually talk to you about a diversity of user perspectives, basically from younger people to people with disabilities. We've looked at how they think about and interact with autonomous vehicles at every level, and that's what I'm going to try to walk us through today. So Tony mentioned that the name of my lab is NHanCE, and I remember when I first joined Purdue, I took about 2 months to come up with a clever name, though some people think it's too long. I don't care. In my opinion, it gives a really good feeling that we're trying to enhance human performance. So if I sum this up, what we're really interested in is evaluating and through interface design or redesign, enhancing performance of human operators in a variety of complex environments. So you can see some of the images that I have here in aviation, in manufacturing operations, in healthcare, and of course in driving. And we've got special emphasis on older populations. Here I'm just broadening it to say different age groups, and you'll see why that is an interest of mine later on. But I'll start off by saying, number one, both of my parents are older than 65 and are still working. So some of the questions that they have about technologies, some of the things that they struggle with, I bring to my research and try to figure out how can I help them and people who are like them. That's number one. But number two is that if I'm fortunate enough, I'll one day be over 65. And so I want to be working on things and doing meaningful things that someone else in 40, 50 years from now will actually try to replicate or even enhance when I'm in my kind of later stages of life, okay? And so we'll talk a little bit more about the aging aspect, but I wanted to at least get that started. Over the years, I've kind of put my research projects into at least 4 different categories. When I graduated from the University of Michigan, I was doing a lot with context-sensitive displays. So that's basically speech interfaces, multimodal displays, adaptive interfaces that are sensitive to context and user. So we're still working in the area, but that's kind of what got me started. We've shifted since I've been at Purdue to think about autonomous systems and how humans interact with those, as well as what people are coining cyber-physical and human systems. I added the human. Some people say cyber-physical systems. We're going to say CPHS. Make sure the human is in there. And so a lot of what I'm talking about is in that category. We've also had studies where we've looked at technology acceptance and trust. So my advisor, Nadine Sarter, used to say it's one it makes no sense for a person to develop a technology if people don't ultimately use it. And so really thinking about what are the factors that motivate a person to use it or dissuade them from using it. And some people have landed on trust when we talk about complexity of technologies. And then the final bin here is this idea of self-perception of task performance. And I added this last because it wasn't until I started working with older adults that I realized some of their resistance to using technology has to do with their own self-perception of their task performance. For example, if they believe that they can drive very well, why does a machine need to do it any better? Okay? So there's really some psychology there that we've been able to tap into. I've been fortunate enough to work across these different domains, even though I showed you the first figure that was aviation, healthcare, driving, and manufacturing. Thank you. Just making sure people were paying attention. But I've been fortunate enough to actually work in these environments as well. So we've expanded some of our work to home and leisure environments. So I had a student who recently looked at older adults and how they use Zoom, WebEx, Microsoft Teams, and did a comparison across platforms. And then I also had a student that graduated last year looking at air traffic control, not air traffic control, TSA personnel, and how they perform when different levels of automation are assisting them, okay? And then we've had a focus group study that actually asked older adults, what are some things that encourage them to use or not use smart speech systems like Alexa, Google Home, Siri, so on and so forth. So this is just kind of the landscape of where my work fits. What I'm going to talk to you about today, though, is autonomous vehicles, and primarily because it is a leading technological development worldwide. And if you look across a lot of fields, not just engineering, psychology, sociology, climate, and atmospheric sciences, they're all talking about and studying different research questions related to this future. And so this is what kind of where I want to situate the work for today. And I'm going to try to be ambitious and talk to you about projects that we've had at each or multiple levels along this continuum, as well as different user groups from younger adults to middle-aged adults to older adults to people with disabilities. So we'll try to make those two things intersect. I do know that there's debate about the utility of this particular taxonomy, but for the sake of this presentation, I'm actually going to use the Society of Automotive Engineers classification of different levels of vehicle automation, where the lowest level is level 0, the person is in complete control. Level 5, the vehicle is in complete control. And then levels 1 through 4 are a mix of the two, where 1 is effectively one system controlling some aspect of the vehicle, where level 4 controls everything, but under occasional circumstances may need the person to intervene. Okay, so this is the taxonomy we're going to be working with, and I'm going to talk about level 1 first. So there are a number of promises of automated vehicles. Okay, one of them is that they're going to reduce drivers' workload, they're going to make our highways safer, they're going to reduce the number of accidents, they're going to extend mobility and autonomy for people with disabilities and older adults. And so the question really is, number one, will the technology actually live up to its promise? And number two, what is that going to look like for the user, for the human? And so when I first got to Purdue back in 2018, this was a study that we did where we started off at a low level of vehicle automation. And here we're just going to be concentrating on adaptive cruise control features and lane keeping assistance. Okay? And so, of course, the adaptive cruise control feature is one where you set your speed limit to be at 70 miles an hour, for example. And then if your vehicle encounters a vehicle traveling at a slower speed in front of it, then it'll actually slow down to that slower speed. And once there's enough headway between you and the vehicle in front of you, it will go back to the programmed speed. Okay, and then a lane keeping assisted system is actually one that traces the lane markings and keeps you centered in the lane. So there is literature that talks about both of these systems can increase a driver's workload if a person is vigilant and monitors the automation all the time. And so some people say, well, what's the point of doing that if I'm supposed to be offloading tasks from the human. And then the other one is, or the other perspective is that it can actually decrease workload if the person relieves themselves of the cognitive and physical activities associated with controlling those aspects of the vehicle. Okay? So we know that workload can be decreased, but we also know that if a person engages in a non-driving related secondary task, we call that an NDRT, then that workload might actually go back up. And so here we were trying to pull apart, well, if automation, low-level automation reduces workload, does engagement in a secondary task actually increase the workload back up to the point that it would have been if they had not been using the automated system at all? And so we had a general research goal here was to determine how workload is affected by engagement in NDRTs while using these low levels of vehicle automation. This is the setup that we've got in our lab. I've told some people this already this morning. This used to be NADS, and it was a lot easier to say, National Advanced Driving Simulator, but I think within the next few weeks, they're actually going to be changing their name to Driving Safety Research Institute. They told me that they're not going to try to pronounce this as DESRI. Some people have said, so I got to get used to that. But we do have this mini sim, which is a medium fidelity, fixed-based driving sim that simulates activities of driving. Okay, we've got a heart rate monitor that actually is attached to the person's torso, and it fits just around here. It's supposed to not be intrusive, but it actually monitors heart rate, and from heart rate we can calculate a number of different other metrics. And then we had a button that we attached to people's fingers for them to give us response for this task that I'm going to talk about in just a second. Okay, so how did we actually, or what did the study look like? So there were 3 different automation type conditions. So there was a manual case where the person was in complete control of the vehicle and they had to control speed and steering. Okay, there was an ACC, adaptive cruise control condition, where the vehicle took care of speed, but the person had to control steering. And then there was a lane keeping assistance system where the vehicle controlled lane position, but the person needed to control speed. And to make the driving task a little challenging, we actually introduced these obstacles. So to the manual case, we implemented random speed changes to the lead vehicle such that the person would have to be alert to how close to the person in front of them they were to adjust their own speed. And we also had random wind gusts to make steering a little bit difficult. But we designed both of those tasks to have the same level of workload to not introduce a confound. So in other words, the workload that was associated with speed changes equals the workload that was associated with wind gusts when steering. Okay? And so we had 3 conditions where people needed to control some aspect of the vehicle. So that was the driving task. We also had a secondary task which simulated an NDRT. So somebody who's having a cell phone conversation or thinking of a to-do list, we actually simulated this with something known as the in-back task, which is primarily used in psychology. But the idea is that the person has to remember digits that they've heard in the past and actually press the button, if you remember on the slide before, press the button on their finger, indicating to us when they actually matched the digit in their head with the digit that they were supposed to. So example, we had a baseline condition where there was no secondary task. We had what we called an easy task condition where the person heard a string of numbers and they needed to press the button when the number appeared directly after, when the target digit appeared directly after the digit that they heard, right? So in this case, they were supposed to hear 9, or 9 was the digit that they were supposed to identify. So as soon as they heard it happen immediately after 9 was presented, they needed to press yes. And then the same here, 3, once they heard 3 repeated, they needed to press yes. So we said that this was kind of low workload. When it comes to the 3-back, the person had to actually remember the digit happening 3 digits ago. And so there are a number of studies that have showed that this is actually pretty difficult for people. If you don't believe me, I can put you in the simulator and have you explore this. But we know that that is actually the case, okay? So we put this all together, and we had a total of 25 participants in the experiment. These were all young people. Most of them were students at Purdue. We had our 3 automation conditions and our 3 secondary task conditions, so a total of 9. And then we measured a variety of different dependent measures. So driving-related measures, headway, that's the distance between the subject vehicle and a lead vehicle. Standard deviation of speed, standard deviation of lane position, and then some heart rate variability measures. Okay? For the sake of time, I'm just going to go through some of the trends that we saw. So what you can see here is I'm plotting manual condition when the person was controlling speed and lane position versus when the person needed to control just lane position. And what we see is that as the secondary task, that in-back task increased, the variance in their lane deviation actually became more stable. So one would pause at this and say, well, that doesn't make sense. It would seem like if the secondary task was getting more difficult, the person should actually their driving performance should be worse. We'll talk about that in just a second. But we saw something very similar when it came to deviation in the vehicle speed. So when the person was needing to control speed, the standard deviation of their speed decreased as the secondary in-back task became more difficult. Okay? So this is what happened to driving performance. When we look at what happened to heart rate, this is not supposed to be animated. When we look at what happened to heart rate, we're actually looking at heart rate variability. In the literature, it is the one that's mostly associated with or is most sensitive to changes in workload. So what we see is a very similar trend that as the secondary task increased, the difficulty of the secondary task, so did the person's heart rate variability. And in this case, a lower heart rate variability signifies higher workload. Okay? And we saw the same with a different measure, RMSSD, another heart rate variability measure. We also saw that as the secondary task increased, heart rate variability decreased. Okay? What may be going on here? If you're familiar with this Yerkes-Dodson or inverted U performance curve that talks about one's performance as a function of their arousal level, okay, we believe that the secondary task, that the driving task by itself maybe place people closer to less optimum performance in the sense that they might have been bored. Okay? Whereas as you add some type of stimulating task to the monotonous driving task, we're actually bringing them closer to their optimum arousal level. This is just one speculation that we've got. We've seen some other studies that actually maybe make the same claim. Okay? So there's something to be said about the fact that as you automate more functions of the vehicle, okay, you're decreasing a person's workload, but that workload may be being increased again with the introduction of some secondary non-driving related tasks. Okay, that's study 1. Second study that I want to talk to you about is actually at level 3, which is where the vehicle is controlling both speed and lane position, and to some extent can monitor or can actually start and stop, and can turn corners, so on and so forth. And there is a lot of interest around this construct of situation awareness. Okay, and so if a person is to some extent relieved of having to monitor steering and speed and engage in non-driving related secondary tasks, there are questions around what is the knowledge in a person's head at a given time. And so there's this construct that came out in the early 90s, Micah Inslee, that's known as situation awareness. And what the proposal says is that there are at least 3 levels of situation awareness that will tell you something about what a person knows at a given time. So the first is that the person has to perceive objects and elements that are in the environment. That's the most basic level, level 1. Level 2 says that they must comprehend those objects, and level 3 says that they must be able to predict their future state. Okay, and so the way that we actually go about assessing situation awareness traditionally is either through some type of subjective questionnaire where you ask people after some interaction about their level of knowledge regarding the interaction. Or you probe them in real time as they're performing some tasks. You actually ask them task-related questions. And there's a third one where the person actually completes the task and you ask them a series of questions similar to the first subjective one that I talked about. Okay? So those are kind of the gold standard methods that we have for assessing situation awareness. But we actually worked with the Ford Motor Company who wanted to go a little bit beyond that and say, well, rather than using these paper-based and post hoc methods for assessing situation awareness, can we actually use physiology? For example, eye tracking or heart rate monitoring, brain activity, and can any fusion of that data tell us anything about what a person knows? Okay, and so for us to get this work started, we actually did a systematic literature review. We didn't realize it would turn into a systematic review. Well, we actually identified a total of 25 studies that had mentioned some type of correlation or association of situation awareness measures, those direct measures, and have tried to map those onto some physiological measure. Okay, so you can see that the number in parentheses represents the number of studies that we found in the category. Okay, and so you can see that the majority of studies actually used eye tracking and tried to associate that with SA. The second majority was heart-related measures, but the findings were so mixed that we actually couldn't glean anything informative for us to include in our own experiment. Respiration rate, there was just one, and then electrodermal, there was just one, so not enough to really make any conclusions. Although there were few for electroencephalography, which is related to brain activity, although there were few, the results there did show some promise for being sensitive to changes in situation awareness. So I'm just showing you a table here that talks about those 16 different eye tracking studies. And what they found was that you can actually classify eye tracking metrics into two different categories. Okay, one of them is known as unconscious, and the other one is conscious. So when we talk about unconscious eye tracking measures, we're talking about those that the person cannot actually control or per se. So blink rate, pupil dilation. Okay, those are the two that are listed here. Okay, frequency of blink. Okay, those are things that traditionally people are not able to control. But there's a whole set of what we call conscious measures that deal with how a person scans the environment, where they're looking, and for how long they're looking. And those were the ones that actually were more associated with situation awareness. Okay, so we had this research goal to determine whether pre-takeover request, I'll talk about this in a second, so how someone allocates their visual attention before an automated vehicle asks them to take over control, if that has any influence on a person's post-takeover request situation awareness. That's the question we were trying to answer here, and we were going to assess that using eye tracking. Okay? So we actually set up an experiment where there were 3 different types of secondary task conditions. One of them is what we call a monitoring condition, where we actually did not control how people allocated their attention. So basically they could have looked at the screen or they could have looked down, but we did not allow them to interact with secondary devices. So they couldn't take out their cell phone, but they could certainly visually look wherever they wanted. We also have something known as the peripheral detection task, a second task condition where we actually tried to force people's engagement to be always on the screen. So what does that mean? There were 2 dots that appeared in either one of these squares, and once the person recognized or detected the dot, they had to press a button on the steering wheel, letting us know that they saw it. And then we had a SURT, or CERT, surrogate reference task, which was actually on an iPad off to the side of the vehicle, where we tried to control people's attention to be completely off of the screen. So a mix of 3 conditions, one where they could do whatever they want, one where their attention had to be on the screen, and another where the attention had to be off of the screen. Exactly. Okay? And so how did we do this? We put people in a driving sim. We had them drive for about 7 minutes, interacting with these secondary tasks. And then at some point, they got a takeover alert, and they were instructed to, as soon as they got the alert, to pay attention to what was in the surroundings. And because we were going to be giving them, sorry, my student did all of this animation. So because we were going to be asking them questions about what they had just seen in the 7-second time window after the takeover request, okay? And so this is kind of summing this up. They were engaged in each one of these tasks for a certain amount of time, and then there was a second observation window where they were asked to pay attention to what was happening, and we wanted to assess how much they knew. Okay, here's the summary. So we used what we call a SAGAT. It is the Situation Awareness Global Assessment Technique, which is a list of questions that ask people about what was happening in the environment, where you freeze the simulation and ask them those questions only after that. Okay? What we see is that when a person's attention was off of the road, their essay score was the lowest. Okay? When they were able to decide how to allocate their attention, medium. And then when they were forced to engage with the driving task, the highest level of essay. Okay, and one may say, well, this is kind of axiomatic, right? We could have expected that, but we needed that actually for ground truth. Okay, so we seem to be good with essay score, that our conditions did put people in the right situation awareness frame, mindset. We actually looked at then a host of eye tracking metrics. So the spatial density is just one of a number of conscious eye tracking metrics. And the technical definition is basically, if you can think about the driving simulator being divided into a number of cells, this is the number of cells that contains at least one gaze point, okay, divided by the total number of grid cells there are. So this is really location-based, but also a spatial measurement, right? And so what we saw here when it came to spatial density, that their spatial density score increased also as in a similar way that the essay score did. And so that's telling us that so the more that they seem to know after the TOR reflects where are the number of cells that they were scanning after the TOR. Okay? What I want to show here is that in summary, there are a host of metrics that we looked at. This is just a set of them that are related to duration and location. So duration deals with the amount of time for which a person spent looking at the screen, and location deals with exactly where people were looking. Okay, and the summary that we take from this is that when it comes to location-based metrics, they were the ones that were mostly associated with changes in situation awareness. Okay, so what does this mean for a company like Ford that came to us and wanted to answer this research question? Is that if they're interested in possibly assessing a person's essay, they may want to look at these location-based eye tracking metrics. Okay, some of you may be interested in this. We had a student working on this project who wanted to see if we could actually predict high or low essay, okay, based on a fusion of eye tracking data that I just talked about, as well as EEG data that the student collected. And so I don't talk much about EEG here. That's not my background, so I'm not going to try to pretend that it is. But what she found here is that, first of all, she used two different ground truth labeling strategies. One is the generic way that we would label essay or workload, where you just take the value, so you average the values, and you use the values that are lower than 50% to be low essay, use the values higher than 50% to be high essay. But she said, well, is there a way that we can actually remove those middle boundary values, where we use a 40-60 split instead, where we use values less than the 40th percentile and values greater than the 60th percentile, and deem those as low to high essay. And what she did was tested 5 different machine learning classifiers, and found that the neural network produced the best performance. Okay, so you can see the summary stats here. And then when she actually looked at what happened when you look at the EEG features alone versus the eye tracking features alone versus the fusion of the two measures, okay, the combined approach actually resulted in the highest or best performance. Okay, and so from this, she actually went forward with the neural network model, and she plotted out, again, sorry for the animations, she plotted out this feature importance plot where she found that the optimum number of features for this data set was 11. And it was a combination of, you can see eye tracking metrics here in yellow, and then EEG metrics in blue. So it was a combination of the two, and this is the results from the confusion matrix. Okay, so once we add features beyond 11, the model's performance actually started to decline. Okay, and so the highest accuracy value we were able to achieve was 90.6. And okay, the second study that I want to talk to you about at level 3 is related to older adults. Okay, and so some people may be asking me why older adults? Why older adults? Well, I introduced this at the very beginning of the presentation about my parents, myself. Okay, but we also know worldwide that people who are 65 and older are actually the fastest growing age group worldwide. And we actually reached an inflection point that in 2016, so this is the year I finished my PhD, there were more people 65 and older than there were kids between the ages of 0 to 4. So that's something to think about. Okay, that's got a whole lot of societal and what we call gerontechnological implications. Okay, one of those being that we see that there's this infiltration of autonomous and sophisticated technologies in a number of environments that we operate in. Okay, so not only will there be more and more older people living longer, but they're going to be interacting with a variety of increasingly intelligent technologies in later stages of life. And so if you look at some of the demographic or population statistics, you'll see that in just 7 years from now, the convergence is somewhere around 20% of the general population being made up of older adults, of the workforce being made up of older adults, as well as the driving population. So a number of societal implications that we need to be thinking about. What I'm showing here is basically what a takeover event looks like. So in summary, the vehicle is driving itself for an extended period of time. At some point, the person receives a takeover alert, a TOR, takeover request, where they've got to redirect their attention from what they're doing in the vehicle to pay attention to what's happening in front of them. And then they actually need to navigate whatever obstacle is in front of them, why the vehicle is asking them to actually take over. And what we know in the literature today is that there are a number of reasons why a person may actually be asked to take over, related to stalled objects that are in front of the person, failure of a GPS signal, system malfunction, missing lane markers, what have you. These are just some of the events for which we know that people may be asked to resume control of the vehicle. And as I mentioned, an in-back task is not very trivial. If you've never done one of these, a takeover task is also not very trivial, depending on what's happening in the environment and what are the things that are demanding your attention, other things. What I wanted to say is that as of May 2022, this was a little disappointing, is that even with all those stats that I just showed you about older adults, there were only a total of 14 studies that had actually looked at older adults and their interaction with autonomous vehicles. Okay, and the majority of them were situated around this takeover paradigm. Okay, 5 of the 14 showed that takeover performance is impaired in terms of efficiency measures. So we would say that that's response time, for example, and the quality of takeover. So once the person is actually back in control, how are they handling the vehicle? And the systematic review that we got this information from explained that there are a number of factors that influence older adults' performance outside of just age, things such as the characteristics of a takeover request. So that's the modality and the timing of the takeover request, okay? The type of non-driving related secondary tasks that they were engaged in, the distribution of driving modes, so which fraction of the drive are they actually driving versus the vehicle is driving, okay, duration of the drive, number of takeovers, so on and so forth. Okay, but there were two things that we actually didn't see identified in the study, is that number one, all of these studies employ different age groupings. So we like to say that 65 and older is the lower limit for what we deem as older, but all of those studies did not necessarily use that same categorization, right? Some say 60, some say 65, some even started them at 70. So there's a lot of work that needs to be done in this area to figure out where convergence is, to make some more conclusive findings about what this space actually looks like, and you really can't do that with 14 studies. And the other one that I won't get into today is this idea of non-chronological age factors. Okay, what that means is that there are a lot of covariates that we can identify that change with a person's age that are not being accounted for in a lot of the studies that we're talking about. Okay, so one of the studies that we actually did, we actually divided this into two different studies. One of them looked at, if we think about the takeover request, if we look at the takeover process, we actually divided it into two phases. So one we call a signal response phase. So that's the time that it takes a person to understand that they have been summoned to take over, and then to position themselves to actually successfully take over control of the vehicle. And then another phase is called the post-takeover phase, where the person is actually in control, and then you can look at metrics around how they handle the vehicle. What I want to talk to you about is that we use the same driving sim, but this time we were interested in filling in gaps related to how you alert older adults. And I think Tony McDonald had a systematic review a few years ago that talked about the need for filling in the gap in terms of the alerting mechanism that you use to signify people of a TOR. And so this actually converges with some of my own expertise. So we actually varied a variety of different signaling modalities: visual, auditory, tactile, and combinations of all three. And so what did that look like? This was a second experiment where we had 24 younger and 24 older adults. We did use 65 to be the lower limit on older adults, where the average age was about 71. And then we had 7 different signal types or TORs represented. So a single visual alert, an auditory alert, a tactile alert, binary combinations of the three, and then one case where all three were presented. Okay, and we also had 4 different secondary task conditions. So a baseline, okay, we asked younger and older people to watch video, a TED Talk video, and afterwards we actually asked them a series of questions. A headway estimation task where we asked them to estimate the distance or the timing between themselves and a vehicle in front of them, and then a combination task where we actually combined the two. So this is what those would have looked like. Okay, in the no secondary task condition, there was nothing for the person to do, and they could determine how they wanted to allocate their attention. Video watching, we placed the video in the lower right-hand corner. Okay, headway estimation, you can see that this is about 3 seconds, 5 seconds, and 7 seconds of headway gap. And so we showed people what this looked like ahead of time and asked them to do this task in real time. And then there was one where they actually had to do both: watch the video and estimate headway. And so I've already said that impact task is difficult, takeover task is difficult. I'm going to say that this was also difficult for people. Okay, what did we find? When it comes to takeover request response times, first of all, we see that the combinations were responded to faster than most of the singles. Okay, so we're not going to advise anybody to use a single visual alert. We're not going to advise anyone to use a single auditory alert. Okay, so the winners, number one, was when you combine all three, visual, auditory, and tactile. Okay, and that's the case for both younger and older adults. But the second thing we saw is that there seems to be an advantage when you combine a vibrotactile signal, okay, with any other signal. Okay, so those are some guidance material that we can give to automotive companies. For example, if they're trying to think about what type of ways should they be alerting their drivers. Okay, when it comes to the different task conditions and how long that took people to respond, okay, it is no surprise that the headway estimation and the combination task condition resulted in the longest response time. So we can see that. But what was really exciting for us is that we've done all this work with situation awareness and eye tracking. This was what was really exciting for us is when we look at what happened with older drivers' attention allocation. Okay, so I've got younger drivers over here, older drivers here, and I'm looking at when we asked them to watch the video, we can see that older drivers tended to try to spread their attention over both the video as well as the roadway environment. And there is some literature that talks about the fact that older adults, as they get older, tend to self-regulate their driving strategies, meaning that they may limit their nighttime driving. They may take more breaks on longer drives. They may limit in-vehicle distractions. Okay, this is something else that we found out was that they actually tend to prioritize safety over entertainment. Maybe that's not a surprise, but the fact that we were able to pick this up with some sensing data actually got us pretty excited. And that was really no different when it comes to the combination task. Okay, I'm going to, for the sake of time, go to the final study here. So that was at level 3. And then this highest level, level 5, okay, this is where the vehicle is in full control. There are some companies that are even talking about not having steering wheel and foot pedals in the vehicle where the person really has no responsibility for ever needing to be in control. So this is where people are saying this is really, 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 really far out. The Department of Transportation knows this, okay? And what we know, if we look at the population demographics, this was surprising to me when I first started doing this work. We've got about 26 million people in the U.S. that got some form of a travel limiting disability, okay? And so if we think about what the population is, somewhere around 330 million. So 26 over 330, that's pretty significant. So we've got a large group of people in the U.S. population that has some kind of travel limiting disability. Most of those are mobility and visual impairments. Either you're in a wheelchair or you've got limited sight or blind. Okay, and we can look at what it looks like when it comes to age group, which older adults do not actually represent the largest portion of people with travel limiting disabilities. So I want to dispel that myth. But when we look at what the literature says about people with travel limiting disabilities, what we see is that they talk about them having difficulty entering and exiting a vehicle, knowing what's happening in the vehicle and around the vehicle as they're getting in and out, not being able to access vehicle controls to change things like entertainment or climate or close the door. Okay, and then just general safety concerns. What happens if I'm on the highway and I get myself in trouble and I need some help and no one is riding with me? Okay, so I'm saying all this to say that in 2020, the U.S. Department of Transportation launched what they call an inclusive design challenge, where they asked for, it could be industry or academia, to put together ideas for a concept autonomous vehicle that people with a wide range of disabilities could use. And in this competition, you could actually focus on any aspect of the vehicle, and you could focus on any type of disability. And so We actually, we formed a team at Purdue. I'll show you the teammates in just a second. We formed a team, and we were named one of the semifinalists for our product. That was in January of 2022. Okay, we started this. We started at the end of 2020, and we had 18 months to build the vehicle. And then just this past summer, we were announced as the first place winners of this competition. And they gave us $1 million to actually explore some ideas that we'll talk about in a second here. Okay? And so those I thought were impressive accomplishments. The most impressive accomplishment, and I've talked to John and Tony about this, was actually having Secretary Pete acknowledge Purdue for winning this competition. Okay? So this was a little bit of a joke, but this is what got me into Twitter. So this is what our vehicle looks like. It's called Easy Rider. It is a mouthful. I did not create this one. I created NHanCE. I promise you I did not create this one. But this is what it looks like. We had it wrapped in the Purdue colors. And what's really neat about this, so these were the different companies that we worked with to pull this off. Brown Ability, they're a local company in Indiana that they have expertise in wheelchair accessible vehicles. Scheffler Paravan, they helped us build interface for people with disabilities to be able to interact with the vehicle. So they said that they can't access controls, so we use speech and touch controls for them to be able to interact with the vehicle. Prehensile Technologies is a company that provides innovative robotics and sensor systems for powered wheelchair users. That company was actually started by a graduate of Purdue, so he joined the team. And then this Locomotors. So a lot of people know them as the developer of one of these commuter shuttles. And what I will tell you is when they talk about challenges during a project, this was one of the first ones I have ever encountered that the company actually closed its doors about 6 months before the competition was done. So you can imagine how we had to pivot to a plan C, and I think I told Robert this earlier, a plan C and to some extent a plan D. But if you look at this, if we add up all of the people who were on the team, we're looking at about 30 to 40 years of experience in accessibility for people with disabilities. This is kind of what the features of the vehicle look like. I was going to show a video, but for the sake of time, I'll just kind of walk through them. We have this smart ingress-egress ramp. We've got a smart ramp deployment system that actually has laser-guided lines, and it knows how to identify the appropriate parking spot on the side of a sidewalk for the person to safely enter and exit the vehicle. Okay, we've got a universal wheelchair securement system. So some people have manual wheelchairs, some people have powered wheelchairs. This system is agnostic to that, and a person, regardless of the type of wheelchair that you've got, can actually navigate themselves in and secure themselves into the vehicle. People don't know this, but if you're in a wheelchair, you actually need to secure that device as the vehicle is moving around. And then we have this awareness system, which was basically 2 TV monitors at the front and the back of the vehicle that displayed a number of things. It had a multi-camera view that showed the person how they were backing into this securement dock. This is where they would actually control their entertainment, climate, lighting, what have you, navigation. All of those things were controlled using both the app on the next slide as well as the monitor that they see here. So Jeff Ackerman is the one who founded the Prehensile Technologies company. That's him. He's demonstrating this. This is the app, but this is what the app looks like. And it can actually be used on a personal tablet, a smartphone, or a watch. And it's got voice recognition capabilities. We wanted to do eye tracking, but we actually didn't get around to being able to do that. Kind of similar to the Samsung Galaxy where you can scroll using your eyes. Okay, we didn't get around to that. What I do want to talk about very quickly, though, is that the way we evaluated this is we had 2 nationwide surveys, one that was generic that just assessed people with disabilities' interest and trust in autonomous vehicles. And then we had a second survey that was specific to our own design. Okay, and you can see the ends for each. This was us working with a number of community partners to get access to this community. We also brought our demonstration to this annual Road School Transportation Conference and Expo that Purdue hosts every year during spring break. So this is why I'm never able to go anywhere fun each March, because I'm having to attend this conference. It usually brings about 3,000 people together, and we were able to have people who have disabilities and don't actually take a look at the vehicle and give us some feedback. And we actually took that feedback and incorporated that in our design. And then the very last thing that we did were these interactive demonstration sessions where we collected both qualitative and quantitative data, mostly around using people or involving people who have mobility impairments and are blind or have limited sight. Okay, these are just some takeaways. So 60% of the nationwide survey, 60% of the people who responded to the nationwide survey said that they would trust an AV if the interior display showed them what the vehicle is planning and seeing. So this is kind of going back to one of the barriers that we identified in terms of them not knowing much about what the vehicle was doing. Okay, and so they said that this would help build their trust. We also saw that 73 and 65% of respondents that was respectively said that they would prefer touchscreens and voice controls as opposed to a number of other modalities that people with disabilities have at their disposal. So we use that to inform the design of our vehicle. And then this was interesting for me, but this does not seem to surprise my colleagues. The vast majority of respondents said that they wanted to be forward-facing. And so the reason that you may say, well, of course they'd like to be, if you think about the design that we've got, we can actually get two wheelchairs in this vehicle, one that's located here and one that's located over here. And so we've designed it such that both can be forward-facing, but if they wanted to have a conversation, they can actually face each other. Okay? So this was the one thing that actually went a little bit against what they were telling us. But if people are talking about ride-sharing in AVs, then we wanted to enable that kind of a future. Here's the final data slide that I've got. These are just some basic metrics that we collected in terms of how long it took someone with mobility impairment or who were blind or visually impaired to actually get into the vehicle and get themselves ready to ride. So this onboarding time included entrance, securement, and positioning, meaning that they said, hands in lap, I'm ready to ride. Okay? So this is about a minute, 1.34 minutes. And then for the person who was blind, about a quarter of a minute. Okay? We also got some pretty good ratings. I promise you we are not inflating this, but we got some pretty good ratings in terms of how they thought about the safety of that entrance ramp and also how accessible that user interface was, as well as just the overall system usability. Okay? With 5 minutes left, this kind of wraps up what I wanted to talk about. So there's a lot of debate about what the state of autonomous vehicle development is. I guess for me it doesn't matter, because what I'm most excited about is the fact that the NHanCE lab and my students together we're able to kind of contribute some knowledge and some guidance to whatever that landscape ends up looking like. There are a ton of things that still need to be answered. One of the things I'm very interested in is this idea of distraction versus engagement. There was a report that I was recently an author on where they're talking about higher levels of vehicle automation, but they're still calling that distraction. Whereas I'm asking the question, if the person's primary role is not driving, why are we still labeling that as distraction instead of disengagement, for example? And so what I've learned, if nothing else, over these last 5 years is language is very important, okay? How you talk about things to make sure everybody knows exactly what it is you're talking about. Trust and automation, there's a lot of work happening in that area. And then this idea of an equitable transportation future. How do we kind of bridge the gap and make sure that the expected promises of AVs actually do map out to something that's realized? Okay, that's all I've got. I could have not done any of this work without the help of my students. We try to do some socials each year, and so these are some of the pictures. We've had several students who've left our lab who are now successfully professors at other universities, some who are working at research institutions, transportation research institutions. A student that just emailed me recently and said she got a job with Boeing working in defense. And so that, as an advisor, also makes me proud. So I know this was long. We're at 12:57, so if there's time for maybe a few questions, I'm happy to take that. Thank you.
Yeah. Thanks for the talk. Thank you. Just a quick question about your situation awareness and the eye tracking. So it seems to me that if the task involves using the eyes, your signal-to-noise ratio is going to be really poor because, even your combined task where you have to look at the screen and the road at the same time, how does that impact your SA measurement?
So you're saying, were we looking at the eye tracking on that secondary task as well?
Well, just in general, if your eyes have to move around, how are you going to measure your situation awareness?
So in this case, once the person got the takeover alert, they were asked to immediately put their attention on the screen. And so we actually started our calculations only once the first fixation was on there.
But if they weren't aware of the takeover, they might be looking at other things, right? I'm just curious if your task is dependent on, if your measurement depends on the task.
I think so, but whether they were looking off to the side of the screen or on, for the things that we calculated, the time clock started once they had a first fixation on the screen after the takeover request. But I think I'm maybe missing something. Okay.
Brandon, just a quick, and just kind of in general, like, so you have these like simulators and just in general about kind of the discipline. And I'm curious, like, because you mentioned something about, you designed this experiment and you found this out that, older adults do such and such, which for me, I would call that, there's sort of like, confounds the relationship between the intervention you're implementing and the thing you're trying to measure. And so I'm curious about, like, just in general, like, design. I know it's hard, right, because you have to recruit people, like doing this sort of like in a sort of like a clinical trial sort of time fashion, so you can sort of say, like, this, I don't know, this is a little bit more of my research. Just curious about that.
So your question is, how difficult is it to run these trials?
Yeah, like, how do you, if there's have you thought about like designing these like as a clinical trial where you say, like, well, I expect these confounders to influence what I'm trying to measure, so I'm gonna like randomize people to this and that, and then I look at the intervention.
That actually is very possible because the way we've been able to recruit older adults and people with disabilities, I mentioned, is by community partnership. So as soon as I got to Purdue and I knew that this was the line of work I wanted to take up, I started figuring out who in the community I could partner with to make this possible. So whenever we've got a study where we need older people, we've already got about 4 or 5 independent living facilities where we say, hey, next study, and then they either put flyers in their mailboxes or they promote the study somehow. And some of those facilities actually have shuttles that will bring people to campus. I think that that's very possible because we've got people who, once they're interested in this, they're kind of indefinitely interested in it. So to set this up as a clinical trial where we bring people in for multiple interventions and evaluations, absolutely.
Thank
you. Okay. If there's no other questions, let's thank Brandon.
Thank you.